All right, so let's try this power model technique with our GoFish example. So the technique says to take the natural log of your x and the natural log of your y. I'm going to create a new table here. I still got my data in here. I mean, it's still in the calculator. I don't need to add to the same spreadsheet. So I'm going to take the natural log of length, and I'll call that one, and I'll call this one ln weight. So let's put this in. I'm going to take the natural log. So now I can't use a column reference because it's not in this spreadsheet's columns. So I just go to vars, and I'll pick the original length variable. Looks like I got a arrow in there, and then take the natural log. What's going on? Natural log of weight. Why is it doing now? Must be hitting control. Gobble gobble. Vars weight. So these are approximations because the raw data had decimals in it, and these are whole numbers or exact values because they were integers. If we want approximations, you can just multiply by 1.0, multiply by a decimal. That'll overwrite those and make them, not that it matters. When you plot it, it doesn't really matter. So let's take a look at the graph of the natural log of length versus the natural log of weight. That's nice and straight, which tells us that a power model is appropriate. Let's run the regression model. If you wanted to look at a residual plot, you certainly could. Option 2, there's a residual plot. Looks good. Maybe even better than the other ones, I don't know. So negative 4.37, 3.05. So my model is the natural log of my weight is equal to negative 4.37 plus 3.05 times the natural log of our length. Now this doesn't look like this power model that we said was y equals ax to the b power, y equals a times x to the b power, or p power. But if we use our properties of logs and exponents, we can put it into this format. That's something I don't think you'll have to do on the AP test, but I do require it on my test, so make sure you know how to do that. So in order to do this, we need to solve it for weight. So let's exponentiate both sides using a base of e, or it, as we sometimes say in our math classes. So that leaves me with this. So how do I handle this entire thing raised to the, or e raised to that entire power? Well, I can separate it into e to the negative 4.37 times e to the 3.05 times the natural log of length. If you're wondering what property I'm using there, I'm using the property that says x squared times x to the 5th is equal to x to the 7th. You guys all know that one. So basically when you multiply powers, you add the exponents. Well, if you have a x to a sum of two numbers in an exponent, you can also write it as a product. So that's what I did here. I went backwards on that. This is just a number. So let's write down that number, e to the negative 4.37. If I hit that vars stat a, that's my, so if I take e to that number, 0.0126, 0.126. Now here, I want this e to undo this logarithm, but I can't do that with this coefficient. If you remember your rules from logs, that coefficient can be put in here to an exponent, and now this e will undo this natural log. Inverse operations. So this undoes this, so you just get length to the 3.05 power. And this is a power model. This is a power model where you don't have a y-intercept, where, you know, whenever you plug in x equals 0, you get you get 0. Okay, so it's going to be slightly different than these other two models because these did not go through the origin. This one will always go through the origin. Okay, and if you notice, the exponent, the power, is basically the slope of your original, of the regression model of your transform data. So this slope becomes your exponent. So this model predicted the best exponent is a 3.05. You might have a little discussion about whether this 3.05 is the best power model or that one where we cubed the length is a better model. It's arguable. Okay? If this transformation straightens out your data set, then a power model is appropriate. Okay? That's kind of the bottom line. All right. That's it. Let's do one more example here. This is using the period of, using the distance from the sun to predict the period that it takes the planet to go around the sun. So here's the distance from the sun in astronomical units. Earth is 1 astronomical unit away from the sun. And here's the period in Earth years. So Earth takes 1 year to go around. Pluto takes 248. Mercury takes about a quarter of our year to go around. So how can we use distance to predict period? So I think I have that data stored on my calculator here, so I don't have to type it in. You can type it in your calculator if you want to follow along. Whatever. Should be under planet. All right, so let's always take a look at your raw data first. Don't start doing transformations until you know a transformation is appropriate. Distance versus period. Looks pretty straight. Analyze, regression, linear. Yeah, I guess you can probably see some curvature there. That's what the residual plot is nice for. It helps us see slight curvatures. Yeah, that's definitely not appropriate. So let's take the natural log of both. Instead of playing around with different powers, let's just take the ln of distance and the ln of the period. This is the natural log of column A. This is the natural log of column B. So let's go back to our linear model here and let's put in natural log of distance and the natural log of period. That certainly straightens out our data much, much better. Unfortunately, and this was what happens when you use real data, if we look at the residual plot, it's not going to look as good as we wish it would. There's still kind of a pattern in the residual plot. Yeah, I don't know. You could certainly say, well, then there must be a better model out there, but physics it tells us that there's not a better model. This is actually the right model. This is maybe just some chance variation that happens to be into a pattern. I don't really know how to explain it other than to say, oh well, we're just going to keep going with it. Sorry. All right, so let's find the model. So we have 0.00025 plus 1.5x. So the natural log of the period predicted is equal to 0.12325 plus 1.5 times the natural log of the distance. So let's put this into that power equation. Y equals a times x to the p power. This undoes that natural log, so the period is equal to e to the 0.12345 times, let's put this 1.5 in as an exponent inside that log, e to the natural log of distance to the 1.5 power. So the period predicted is equal to, let's take e to the 0.005 or 0025, whatever, e to the stat a, that was my y-intercept, 1.00025 Then this undoes that, so we have distance to the 1.5 power. And what I was shooting for here is for an aha moment for all of you physics people to say, oh yeah, I remember this. This is one of Kepler's laws. I think Kepler said that the period squared is proportional to the distance cubed. Well, that's the period is equal to distance to the 3/2 power, or distance to the 1.5 power. This is Kepler's law. But in class, nobody recognized it, so you're watching this video, maybe you'll recognize it, maybe you don't. Regardless, though, it would have taken us maybe considerable time to try to find the right power to use here. I might have squared the distance, square rooted the distance, cubed it. You know, how would you have found the 1.5 power? This model finds the power for you. Astronomers discovered a new planet called Eris. It's about the same size as Pluto and is located 9.5 billion miles from the sun. That's 67.781 astronomical units. So let's find the period, the predicted period of this new planet. So just take 67.781 to the 1.5 power. 558, about 558 year period. So that means it takes almost half a millennia just for the planet to go around the sun one time. And then this is just a little FYI about planets and stuff. Okay? Power model. It's kind of nice. It's kind of neat. It's pretty easy. So use it.